Alright, so in the last video we looked at a resistive load, right, which was just a resistor connected in series to a sinusoidally varying EMF. That's a mouthful. Now we're going to look at a capacitor connected in series to a time varying sinusoidal EMF, right? Basically an AC battery. So again, it operates the same way, right? A closed current loop that's rotating in an external magnetic field. For now, or from now on, I'll just write that as basically that, right? That up and down should show you that that's a AC battery, and that's connected to, well, in this case, a capacitor of some capacitance C. That's it, right? So that generates a current, I'll call I, and that's a very simple circuit. So we have a relatively simple Kirchhoff's loop rule, which has the EMF minus the voltage drop across the capacitor, which I'll keep as V sub C. And that equals 0. Okay? So these are obviously equal to one another. And so we can write that as, well, the EMF varies sinusoidally, right? Which can be written like this: some maximum voltage times sine of the driving angular frequency times time. And that's equal to what your book has as lowercase VC, right? The lowercase is as a function of time. Uppercase is the constant, right? The uppercase V in this case, I'll try and write it like that, is the maximum voltage across the capacitor. So then that also has to vary as a function of that frequency, right, and time. That's kind of a silly nomenclature, right, the lowercase and the uppercase. I don't want to introduce another type of nomenclature here, so I'll just try and stick with that. So lowercase, small, uppercase, big, right, and those are subscript C's. All right, good enough. Okay, so this is the voltage across that capacitor at any time, right? At any time. So again, we want to compare the form of this voltage here with the form for the current across the capacitor, right? Specifically, what's the phase between those two, okay? So remember the general form for the current, general formula for the current as a function of time is, well, we have the current through the capacitor, I'll call I of C, times sine of that omega t minus phi, right? This is always the general form. So we want to try and get the current in this form. So for a capacitor, we don't necessarily know a current outright, but we might know a charge outright, right? We can say a charge as a function of time. So we can start here. This might be the easiest place to start. So Q as a function of t, well, that's some initial charge times sine omega t. I also start at this point, right? There's some amount of charge as a function of time because whatever the voltage in a given time will create a certain amount of charge at that time. So that's another reason I start with Q instead of straight to I. Okay? But they're intimately related, right? We can just take the derivative. So dq dt is simply I. And remember that the charge in a capacitor, Q equals CV, so I'm going to replace Q with CV, and that's a V for the capacitor. And then sine, whoops, I guess I should take the derivative now. Derivative of sine omega t, the omega comes out, omega d, and then times cosine now. Okay, so this is our expression for current across the capacitor. Well, remember that this always has to obey Ohm's law, which remember was V equals IR. So that means if this is a current, this whole thing is a current, this coefficient here also is a current, which means it has to be in the form of voltage over resistance. Right? So this coefficient has to be in the form of some voltage across the capacitor over some resistance. Right? So that means, let's see, what we have is that coefficient, and it has to be in this form. So the voltage cancels out, and I'm going to solve for the resistance, right, through this capacitor or across this capacitor. And actually, in this chapter, we don't have resistance. This is a new variable, a new term, right? We have what's called the reactance. The reactance. Whoops, I can't spell. Too many letters. Go back. The reactance. This is basically the alternating current analog to resistance, right? Just having R was good for like chapter 26 and 27 for direct currents. For AC currents, you need to have reactance, okay? Because current flips and can increase and decrease both directions. So this is chi. And if I remember correctly, chi is spelled C-H-I. So that's the Greek letter chi. Chi sub C. And so that has to equal 1 over omega d C. Okay, and so this is the expression for the reactance of a capacitor. Right? Again, it's the AC equivalent to resistance. So now we can rewrite our current equation. Let's do it over here. And we have voltage over that reactance times the cosine term. Now, this current here, right? We want to compare this current across the capacitor with the voltage across the capacitor up here, right? The coefficients will be different, right? That's just V, this is V over chi. That'll be different because they're different terms, right? One's a voltage and the other's a current. However, that's not necessarily what we're interested in. We're interested in the phase, right? Are they the same phase? Well, that means we need to get them both in terms of sine or both in terms of cosine, right? I'm going to get them both in terms of sine. So that means I need to turn this cosine into a sine. How do we do that? Well, remembering way back into trig, let's see. Am I doing this right? Sine? No, backwards. Of course not. To do that, we need to use the relation, let's say cosine of some angle equals sine of that angle plus pi over 2. So using that, we can turn this current through the resistor into a sine term, but in so doing, we have to change the argument. Now, they're both in terms of sine of stuff and sine of stuff. Now we can accurately compare this stuff to this stuff, okay? And they are different by a phase of negative pi over 2. Negative pi over 2 radians. Why negative pi over 2? Well, so this is the current equation, right? This is the current as a function of time across the capacitor. We need to compare this to the general current expression, which was up here, remember? Current is always this. And so by convention, that negative is in here. But we got a positive. which means that phi up here has to be a negative pi over 2. Negative times negative is positive. So that is what tells me that the phase now is a negative pi over 2. So let's see how that relates to each other in the phasor diagram. All right, let me just erase that real quick. That's the next video. It's my notes. So let's draw a quick sketch. Actually, let me reserve some room. I want to make a couple sketches. This is 1, 2, 3, 4. You'll see what that means shortly. It'll make sense. Just know that that's a function of time. And I'm graphing in both of these cases the voltage and the current across the resistor. Okay. And I want to do this for one complete cycle. So capital T and then half a cycle. Okay, so at the start, let's graph the voltage. Okay, so just some hypothetical voltage amplitude. Oh, blue, that's right. There, something like that. Such that this is V of C. Now red for the current is out of phase by negative pi over 2. Okay, keep that in mind. Negative pi over 2 means that it leads the voltage. So in other words, it's at its maximum amplitude on the vertical axis before the voltage gets a maximum amplitude on the vertical axis, if they're moving left. So if these waves are moving to the left, that means right now current is somewhere like there. Right? And remember, pi halves is 1/4 of one phase. Right? Pi over 2 is 1/4 of one complete 2 pi phase. And so, right here, this is effectively 1/4 of an entire phase. 1, 2, 3, 4. Right? And that's where the voltage is. So that means that the current is back or before, right? It's maximum prior by pi over 2, by 1/4 of a phase. So this then is IC. Now I drew 3 more graphs because I want to show you the entire progression. So now let's graph the next 3 for voltage. Right? So if they're moving to the left, that means this maxima right here will be, well, maximum on the vertical axis. So let's see, let's try and keep the same amplitude. That means it'll cross X at right there, down to a minimum. That was terrible. Let's do it again. There, something like that, right? And the next one, that means it'll be 0 here, and the minimum will be at 1/4. Maximum will be there. There we go. Something like that. And now the minimum will be here. Yeah, that's right. Something like that, right? And so if you take your eyes and go 1, 2, 3, 4, right? Look from left to right. You should see, it should appear that the blue wave is moving to the left, right? Hopefully it appears like that. Let's do the same thing for the red. Let's see, 1/4 phase later, the minima is down here. So it should be coming down right there. There we go. Let's see, 1/2 phase later, the minimum should be here. Okay. And finally, it should be like something like that. There. And so if you do the same thing with your eyes looking from 1, 2, 3, 4, the red hopefully should appear to be moving to the left, right? But more importantly, this maximum is always 1/4 of a phase in front of the blue maximum, right? The current is always in front of the potential, right, for a capacitor. And that's why we can say that the current leads voltage. Okay? And a good memory aid or a mnemonic is ice, right? Keep this in mind for the next video with the inductor, right? This is the current, this is the EMF. So for a capacitive load, C, the current comes before E, right? Current comes before the EMF. And lastly, if we want to write the phasor diagram, we can do that. Let's see, in blue, we have to have the voltage. Let's draw it like this, trying to keep the same amplitude. And in red, the phasor has to be in front by pi halves, which is 1/4 of the way around, right? This is an angle of pi, that's 0, that's pi over 2. So 1/4 of the way around means that it's right there. Okay? And they are, again, phi of negative pi over 2 apart. I know it's not the positive direction like you're used to, but if they're both co-rotating in the counterclockwise direction, they will always maintain this orientation. Okay? The current will always come before the potential if they're rotating counterclockwise, meaning 1/4 of a phase later, that's V, and that's I. Okay, still pi halves apart, and they're still rotating that direction. All right. Okay, sorry that was a long video, but I hope this gives you a good idea of the fact that in a capacitive load, right, for an AC circuit, the current leads the voltage. Thanks for watching.